The previous video in this series, number 8, focused mainly on the idea of the geodesic. However, the final section of it discussed in some detail the rules and relationships which govern the way in which the measured components of vectors can be transformed from one frame of reference to another. It was suggested that those same rules and relationships can be applied to the components of all tensors, and not just vectors, which are tensors of rank 1. In many ways, it's unusual that we've gotten so far in these discussions without a more serious and detailed look at higher rank tensors, or what we often simply call tensors. This was deliberate. We wanted to work through and think through some of the ideas of spatial geometry by using things that were fairly familiar. For example, we looked at two-dimensional spaces for the time being, to keep it simple. We stayed in the main with flat spaces for the time being, to keep it simple. And we considered only scalars and vectors for the time being, to keep it simple. At this point, having more or less sorted out a good number of the rules and relationships that we're going to need in order to deal with some of the mathematics of general relativity, we're now in a better position to introduce higher rank tensors so that the rules and relationships we now have can be applied to them. Tensors are at the heart of general relativity, and so it is vital that we have a reasonable grasp of them and see how those rules and relationships are applied to them and make sense with them. The approach taken here will be a fairly simple one, and certainly wouldn't satisfy a mathematician. Tensors can be discussed and defined from many angles, and a complete picture will not be necessary for us to have. Hopefully what follows should give us a fairly accurate concept of what tensors are, a concept that we can hold in our minds and that will work as we go on to think about general relativity. The first thing to say, I suppose, is that there are many different forms of tensors. They form a family of algebraic objects, and we've already discussed some of them. For example, scalars are perhaps the simplest form of tensors. They are what are known as rank 0 tensors, and we'll discuss them very briefly in a moment. Vectors are also tensors, and are known as rank 1 tensors. And again, we'll give them a quick review before moving on to the third in the family, which are rank 2 tensors and are given the name Dyads. We probably won't go any further than that in terms of things like tensors of rank 3 or more, although they will be touched on at one point. Rank 2 tensors or Dyads are what we're going to be mainly discussing in this video, and even though all of these things are strictly speaking tensors, we will probably revert to simplistic language, calling these scalars, these vectors, and these tensors. So you should bear that in mind. Also, it's worth pointing out here that we are moving towards emphasizing that a very important property of all tensors is that they will remain unchanged even though the frame of reference used to measure them may change. So let's review scalars and vectors with a view to clarifying that simple point before we move on to tensors, or should I say dyads. Scalars, or rank 0 tensors, are perhaps the easiest to discuss. They have magnitude or size, but no direction. Mass, temperature, and energy are often given as examples of scalars. They can't be said to point in any particular direction. And in our discussions, we are likely to be concerned with scalar fields in space, but they still have no direction in space. For example, staying with a flat two-dimensional space, we might picture a scalar field something like this. Let's say we're dealing with a gravitational potential phi in the Newtonian sense. Each point shown here, and the points in between of course, would have a particular value of that gravitational potential. And this value could change from place to place. And these numbers here show how it might change. But there's no direction involved, it's just the gravitational potential energy that a unit mass would have if it were placed at the point. We can obviously measure the position of where a particular scalar value was found by using a frame of reference. And given that this is a flat space, we could use a straightforward Cartesian frame like this. Or if we wanted to, we could use any other kind of coordinate system to measure the position of different values of the scalar field, even a curvilinear frame of reference like this one. Clearly, each frame of reference would give different measurements of what we might call the components of the position of a particular place in the field, which had a particular value of that field. They wouldn't disagree about the value of the field, but rather about the measurement of the position where it had that value. Scalars can be said to be invariant under a change of basis transformation, and as we'll see, that is a property of all tensors. It's obvious here that the field itself doesn't change just because you use a different scale to measure its position, and its value at a particular place in that space would be the same. The measurement of where it is, of course, might well be different, but if we knew the relationship between these two frames of reference, we could easily verify that the position of the various values of the field is exactly the same for each reference frame used. The values of the scalar field in the various places in space have not changed, and all that should be pretty obvious. But what about the Newtonian gravitational field little g that will exist around these points of gravitational potential? This, if you recall, is given by minus the rate of change of gravitational potential with distance or displacement. For simplicity, we'll call the distance x, but in 2 dimensions it would be x1 or x2 or a mixture of both. Would the value from this formula measured to be the same in the new curvilinear system as it did with the Cartesian coordinates? Well, from our discussion in video 7 on the covariant derivative, the simple derivative shown here would probably not measure the derivative of phi to be the same in the curvilinear system. It's not just that the position would be measured differently, that's easy to correct if we know the coordinate relationships, but the value of little g using this derivative could well be measured to be wrong. If you recall, it's all to do with the basis vectors changing in size and direction in the curvilinear coordinate system. However, the covariant derivative of the scalar field phi would take all of that into account and would give the same answer for little g when measured in the curvilinear system. I won't write this out in terms of Christoffel symbols, there'll be more than enough of that later. It's the principle that matters here. Scalars are rank 0 tensors, and that means that they remain the same in any frame of reference. The covariant derivative of a scalar is a vector, which is also therefore a rank 1 tensor, and that also means that it takes the same value in any frame of reference. And this is a very important property of all tensors which should be emphasized. Let's now apply that same kind of thinking then to vectors. Vectors are rank 1 tensors, which are often defined as things with magnitude and direction. We've discussed them a lot, and we have quite a number of important relationships for them already sorted out, with regard to frames of reference and the like. Once again, however, as we move forward, we are likely to be concerned with vector fields in space. So let's imagine a flat 2-dimensional space, but this time with a vector field in it, something like this. You can see here that the field is changing in size and direction from place to place. The arrows vary in length, and they also vary in orientation. Each arrow here represents the field at a particular point, and the point, I'm assuming here, is the center of the arrow rather than at the back end of it. This is for convenience of drawing and positioning. I'll put a black dot in the middle of each arrow to emphasize that fact. Obviously, every point in the space has a field value, but we only show here a certain number of points, and we can measure the position, size, and direction of any vector in this field by using a frame of reference. And given that this is a flat space, we could choose to use a Cartesian frame like this. Or, of course, we could use some sort of curvilinear coordinate system, and again we have at least three things that we can measure for each point in space: the position, the size of the vector there, and its direction in space at that point. It should be obvious to you that the value of the field and its direction at any point does not actually change with a change of reference frame. The straightforward measurements of the position of things, where things are, would be different, of course, because the scales are different. But we understand that if we know the relationship between the two frames of reference, we can easily make the straightforward transformation of the coordinate axes to get the position measures to agree. What would also be different, however, in a slightly more complex way, would be the measured value of the components of the vector, which essentially allow us to find its size and direction. These will change on account of the differing directions of the axes and the differing of their scales, or the sizes of the basis vectors. We discussed this in some detail for the contravariant components of a vector, where we had this formula for 2 dimensions. V equals v1e1 plus v2e2. And this formula says that the actual vector v at a point in the space is the sum of 2 vector components, and unless the field changes with time, this vector v at the point never changes. On the other hand, these measured contravariant components of the vector at that point would probably change in the new frame of reference, because e1 and e2 themselves would change, both in size and in direction, with the twists and turns and stretches of these basis vectors. These things may well change, but this vector v, this rank 1 tensor, does not change when the reference frame is changed. Don't forget that this is a very important property of all tensors, that they remain invariant under a coordinate transformation. They are invariant under a change of basis transformation. Finally, for this vector field, we could ask about the rate of change with respect to displacement of the vector field v at a point. This was the topic of an earlier video, number 7, where we realized that if we took the straightforward derivative or rate of change of a particular component in a particular direction, say dv1 by dx1, then it would in all likelihood be different in different reference frames. This derivative is therefore not a useful derivative for differential equations if we want such things to be independent of the reference frame. However, the covariant derivative, which was written like this, does stay the same, regardless of the frame of reference. You may recall that these uppercase gammas are the Christoffel symbols and contain the metric tensor and some of its derivatives, and these two terms here in 2 dimensions make a correction to the measured derivative of the component of the vector and then produce the actual derivative, the covariant derivative, which does not change from one frame of reference to another. You may also recall that in 2 dimensions this is one of 4 equations for the contravariant components of a vector, and that there are another 4 such equations for the covariant components of the same vector, 8 equations altogether. As a reminder, these 2 sets of 4 equations can be written in the Einstein Summation Convention like this, showing 2 summation equations, each of which represents 4 equations when in 2 dimensions. Remember that these formulae only appear to show one Christoffel symbol term because there is a sum over r, the number of dimensions. This means that each equation will have 2 Christoffel terms when in 2 dimensions, and 3 in 3 dimensions, and so on. Now, the reason for mentioning all of this is that you should start to be accepting the idea that scalars, vectors, and covariant derivatives are all tensors and do not actually change when we move from one frame of reference to another. Granted, some measurements we make on them will be different, but the actual things themselves will not change. Okay, so that concludes a short discussion of rank 0 tensors or scalars and rank 1 tensors or vectors. But what about rank 2 tensors or dyads, which from now on we will probably simply tend to call tensors? What are they? Well, as mentioned earlier, tensors can be defined and introduced in many ways, even via quantum mechanics, or in various types of engineering or computer science, as well, of course, as in pure mathematics. We're interested in only a limited aspect of the idea as it relates to general relativity, but even that is a massive topic which, if treated with mathematical rigour, could involve many hours of studying and working through many proofs and examples in order to gain real clarity and accuracy. The approach taken in what follows will ignore much of that detail. It will inevitably cut corners, and although that means it is fairly narrow in approach, it should give us a reasonably solid idea of what a tensor is, at least in terms of the way we need to use the idea later in general relativity. As a starter, consider once again a straightforward vector field V in a two-dimensional flat space, where each point in space has a possibly different magnitude and direction of the continuously changing vector field. It's shown here once again with brown arrows, although this time, to save clutter, we will not give them their black dot at the centre. Just remember that the vector represented by the arrow is at a point at the centre of the arrow. For these two dimensions, the field vector will be some function of position, namely of x1 and x2, in some frame of reference, and we will probably express it something like this, where this v is the vector field, and this v is meant to represent the function needed to produce it from the x1 and x2. We'll assume that we're using some frame of reference or other, although I won't draw it in this diagram. If we consider one point in this space, with particular values of x1 and x2 in that frame, there could be said to be two numbers representing the vector at that point, namely its components with respect to the two axes of the frame of reference being used. These numbers could either be given as the two contravariant components of the vector at that point with upper indices, or its two covariant components with lower indices. We wouldn't, of course, need all four numbers to stipulate the vector, so let's pick just two here and think in terms of the more usual contravariant components. In that case, for a particular point in this two-dimensional space, we could write for the vector v at that place the formula v equals v1 e1 plus v2 e2, where e1 and e2 are the basis vectors at that point in the frame of reference being used, and v1 and v2 are the contravariant or upper components measured using that frame of reference. More generally, we could write this formula, of course, in the summation form as v equals vn en, which I suppose is applicable to any number of dimensions. And all that should be quite straightforward by now, I hope. However, consider a situation where we have two different vector fields in the same two-dimensional space, something like this, where the second field vector, call it w, is shown here with yellow arrows. This second field could be an entirely different type of field, and can also change continuously in size and direction from place to place, and in a different way to the first field. We can write this second vector in terms of its components like this: w equals w1 e1 plus w2 e2, or of course in the summation convention w equals wn en. In dealing with the mathematics of these two things together, we could conceivably simply treat the two fields v and w as distinct mathematical entities, as separate vectors. But it turns out that it is often convenient to combine them in some way into what is called a dyad, or what I'm loosely going to call a tensor. This tensor could be obtained by taking what we call the tensor product of the two vectors, and the result of that, as you'll see in a moment, will produce what will look like a 2x2 matrix for these two dimensions. It's not a straightforward matrix, however, because just like the metric tensor, it will have varying values at different points in space, and it will transform in a very particular way. This tensor, or dyad, will be able to be manipulated much more conveniently in the mathematics of general relativity than can two separate vectors. So what do we mean then by the tensor product, and what does one look like? Well, sticking with our two-dimensional space, we know that as separate vector fields, v and w are each likely to vary in some way over x1 and x2, and so we could write these as functions. We also know, of course, that in any particular two-dimensional frame of reference, we could write the vectors in terms of their contravarying components and the basis vectors of the particular frame, like this, where this is the summation form, v equals vn en and w equals wn en. So the question now is, what do we mean by the tensor product of these two vectors? We know all about the dot product of two vectors, which is sometimes called the inner product, and which would produce a scalar as the result. This times this gives this. Now you may notice here that for simplicity I've not followed the new rules for vector multiplication, and I've shown a simplistic dot product whereby I've ended up with upper indices for both in the result. That was just for convenience. The dot product is one kind of product that we can get from two vectors. Hopefully we also know about a second way in which two vectors can be multiplied together, and this is known as the cross product or vector product. The use of the cross product can be shown using a simple cross between the two vectors, and so it is usually written like this, v cross w. But unfortunately I can't really illustrate more about this because we only have two dimensions here, and the cross product of v and w would produce a vector at right angles to them both into a third dimension, which we haven't got in this particular picture, so I won't go over all of that. Because the important thing here is that there's a very important third way of multiplying two vectors together, and this is via what is called the tensor product, or sometimes the outer product. This multiplication produces a tensor which we will call T. The use of the tensor product can be shown with a cross in a circle like this, v tensor product w equals the tensor T. Now let me simply state how this multiplication would be done and what the outcome would look like, and then try to make it seem reasonable. In contrast to the dot product or inner product, it's normal to write the tensor product of the vectors v and w for this two-dimensional situation with the first vector v as a column and the second vector w as a row. And the process of multiplication is then different to what you might be used to. The process is that the component v1 would first multiply each of these components of w, and the result would make the first row of a tensor. Then v2 would multiply them and make the second row of the tensor. In two dimensions, we would therefore end up with a 2x2 tensor with 4 numbers in it, and each of those numbers would be a scalar. And of course they could vary from place to place as the components of the vector v and w vary throughout the space. The 4 numbers would also, of course, change if the reference frame, the measuring system, were to be changed, and this is on account of the fact that they are made up of the measured components of the vectors, the two vectors, which themselves can change when the reference frame changes. However, the fact that this particular tensor is made from two vectors, the actual sizes of which do not change under any such transformation, should help to persuade you that the resultant tensor cannot change, even though individually its 4 measured components can when changing from one reference frame to another. Note also that on account of the fact that we chose, in this particular case, to represent the vectors in terms of their contravariant components, those with upper indices, the tensor from this particular tensor product will be written with 2 upper indices, and we could replace the 4 VW scalar expressions inside the matrix brackets with indexed t's, like this. We would usually write the tensor simply as Tmn equals T11, T12, T21, T22, where you can see that this is really representing the tensor components. So this tensor product of 2 vectors in 2 dimensions is a bit like a 2 by 2 matrix of numbers, in a similar way to the 4 numbers that we had for the metric tensor in 2 dimensions. However, the tensor T, just like the metric tensor, is not simply a 2 by 2 matrix of numbers. For one thing, each of the 4 numbers may well vary from place to place in the space. They are not necessarily constants. More important, as mentioned above, is the way in which they transform from one frame of reference to another. We said about vectors that the measured components may change when the reference frame is changed, but the vector itself does not. And that is a very important property of all tensors, whether scalars, vectors, dyads, or whatever. They are invariant under a change of basis transformation. So as far as this new tensor is concerned, Tmn, whilst its 4 components may well change under some change in the frame of reference, the actual tensor T will stay the same, and this can be proved. Now, it is perhaps difficult at this stage for us to see how such tensors could fit into equations and for us to see what that would mean. We're fine with vectors in equations, but if we saw an equation with a tensor in it, or more than one tensor in it, it would not be easy at this stage to appreciate exactly what it meant. Hopefully, as we discuss them further, some useful appreciation of that kind of thing will emerge. Multiplying vectors together via the tensor product, however, is just one way in which tensors, or strictly dyads in this case, can come about, and we'll talk about some other ways later. However, it's worth saying here that the tensor product multiplication of vector v by vector w could have been done differently. When we did it a moment ago, we took expressions for the vectors which each contained their contravariant components, those with upper indices. And so we obtained a tensor with 2 contravariant or upper indices. However, either one or both of the vectors could have been written in such a way that it used their covariant or lower vector components, and this would be reflected in the resulting tensor. If you recall from video 4, the covariant components of a vector were related to the contravariant components like this: Vn equals Vm times Gmn. And it is entirely possible to write out either or both of the vectors v and w instead of like this with contravariant or upper components, but rather with covariant or lower components along with the metric tensor. And if some mixture of the 2 versions of the vectors were then multiplied together via the tensor product, it means we could have multiplied different combinations of contravariant upper and covariant lower components when finding the tensor product of v by w. That means that the same multiplication of vectors could have produced not only this, which is what we had, but also this, where T11 comes from V1 upper and W1 lower, and so on. Or it could be this, where it used V1 lower and W1 upper, etc. Or even this, where both lower forms were used for both V and W. These all, in some ways, represent the same tensor, at least in as much as they were created from the same 2 vectors. However, they are different from one another in some very important ways. For one thing, the 4 numbers in each of them will have been created from the multiplication of different components of the 2 vectors, contravariant or covariant components, so that at a particular point in space, the four numbers in one version of the tensor will probably be different from those in another. However, another extremely important way in which they differ from one another will be the way they transform from one frame of reference to another. They will require different mathematical manipulations. We know, for instance, that covariant or lower components of vectors transform differently to contravariant or upper components of vectors. And so these tensors, having different covariant and contravariant components within the four numbers contained in them, will require care in moving from one frame of reference to another. As a reminder, you may recall that in the last video, number 8, we looked at the equations for the transformations of the various components of vectors, and in transforming what we called the red frame of reference to the blue tilde frame of reference, we ended up with the following equations written here in summation form. This was the transformation equation for the contravariant or upper components of the vector going from the red to the blue tilde frame. And this was the transformation equation for the covariant or lower components of the vector going in the same direction from red to blue tilde. You should be beginning to be able to read these summation equations by now. This one, in 3 dimensions, represents 3 equations because of the m going from 1 to 3. But each equation has 3 terms in it because of this implied sum in n. This equation tells you how the measurements of the contravariant or upper components of a vector will change when going from the red to the blue tilde frame. Here are the 3 equations for the contravariant components that this summation represents. This, on the other hand, which has the derivative the other way round, dxn by dxm tilde, tells you how the measured covariant components of a vector will change when going from the red to the blue tilde frame. And in 3 dimensions, it represents a different set of 3 equations. Therefore, if we are working in 3 dimensions and have a tensor whose 9 components can, in a simplistic sense, be said to be made up of vector components, we will have to transform its tensor components accordingly. So let's take as an example this version of the tensor T in 3 dimensions, a tensor formed from the contravariant or upper components of each of the 2 vectors v and w, given here in red so that we can more clearly see how the measurements will transform into what will be the blue tilde frame of reference. I think it should be obvious that if we wanted to transform it to that blue frame, we would need to multiply each of the 9 tensor components by the relevant differential factor twice. Once for the first index relating to the vector v, and once for the second index relating to the vector w. In this case, therefore, because they are both upper indices, it will need the same multiplying differential factor twice. This box with the same factor shown twice is just schematic. These 2 factors cannot each use m and n, but never mind that for the moment. This diagram is an illustration and it's meant to depict taking the original red tensor, applying in this case the same transformation on each of the 9 components twice, and ending up with the transformed tensor coordinates in the blue tilde frame of reference. The mathematical way to write this correctly would be, in the summation convention, like this, where in 3 dimensions m, n, p and q each run from 1 to 3. Now there are quite a few sums here, as you'll see when we expand things in a moment, but before we do that, you should realise that if we started with a tensor which could be said to have been created from the contravariant upper components of the first vector v and the covariant lower components of the second vector w, then it would be written like this in the red frame, each component of the tensor having an upper and a lower index. And we could illustrate the transformation to the blue tilde frame like this, where we would have to multiply each of the 9 components of the red tensor by 2 different differential terms. Again, the m and n in this box are simply for illustration, but notice that these differentials are the opposite of one another. The first is converting the contravariant upper part of the tensor components, and the second is converting the covariant or lower part. And again, the mathematical way to depict this transformation is like this, where once again the indices p and q have been added so that the various summations can be made correctly. Notice once more that in this case, these are a kind of upside down of one another. Altogether, of course, there is the possibility of 4 ways of transforming a rank 2 tensor or dyad, depending on the indices of the tensor, and they are these. Now let me focus on the second of these for the moment, in order to illustrate how this transformation might actually be done. Clearly, in 3 dimensions, each of the 9 components would have to be multiplied by these 2 differential terms. But of course, it's not just a simple multiplication. For example, going back to straightforward vectors, finding the new contravariant component of a vector using this formula involves taking sums, so that even taking m equal to 1 for the first component v1 tilde, it involved 3 terms which included bits of the red v1, v2 and v3 and was given by this. And that means that in the transformation of this tensor, therefore, the calculations for each of these blue t tilde components will be quite involved. For example, if we put m and n both equal to 1, we will get the calculation for the blue t11 tilde, the one in the top left-hand corner of the result. If we now, for illustration, imagine splitting the tensor up into 2 vectors, v and w, it would be this. And we can now apply this to this and this to this, taking the appropriate sums as we do, and we would get these 2 terms multiplied together. This represents the new blue v1 tilde, which contains elements of all the old red components, and this represents the new blue w1 tilde, and again contains elements of the old red components of w. You should notice that this looks like the upside down of this as we expect. I won't say it's the inverse because with partial derivative differentials that's not the case. So there is the expression for finding the blue v1 tilde from the red v's, its contravariant components. And there is the expression for finding the blue w1 tilde from the red w's, its covariant components. Multiplying these 2 brackets together would give us the result for the blue t11 tilde component, the one in the top left-hand corner of the 3x3 tensor. And it's not trivial. Multiplying these 2 brackets out gives us 9 terms. And that's just for one of the 9 measured components of the new blue tensor, the t11 tilde in the top left. Of course, these VWs all over the place are the old red tensor components, and so we could replace them by t's with the appropriate indices, which would then give the final result for the blue t11 tilde component as this. So, it turns out that this one component of the new transformed tensor contains converted elements of all 9 of the original red components of the tensor. As I say, that's just for t11 in the top left-hand corner of the new tensor. We would have to do all of that 9 times to get all 9 of the blue t tilde components of the tensor t. What a mess. Imagine 4 dimensions, and imagine calculating all 16 components of the transformed tensor, where each of the 16 components would have 16 terms. Now, fortunately, we won't actually need to do all that. We need to understand the principle, of course, and we need to see how it can all be encapsulated in the Einstein Summation Convention very simply. Here is that simplified equation once again for the tensor with one upper and one lower index, giving its measured components in the blue tilde frame calculated from those components in the red frame. And this equation applies whether you have 2, 3 or more dimensions, and it deals with all of the components. Now, for those a little unsure about working through the Einstein Convention equation, such as this one, let's take a moment to make sure we can appreciate the meaning of this whole summation equation for a tensor with one upper and one lower index. Consider again, for example, the calculation of that one in the corner, the T11 tilde, the new component in the upper left-hand corner. How would you show what it was from this summation formula? Well, the first thing to do, of course, if we want T11 tilde, would be to make m and n both equal to 1, which would then give us this. And we can now see more clearly that there are two sums on the right-hand side, 1 over p and 1 over q, each going from 1 to 3 for our 3 dimensions. When you have two intermingled sums like that, it means that the result will give us 9 contributions for this one component, T11 tilde. And here's that result again. And I hope you can appreciate how the two intermingling sums worked out. The p sum gives the 3 rows, 1, 2 and 3. But within each row, the q sum gives the 3 terms in that row, 1, 2 and 3. And this particular example is fairly simple if you think about it. However, it all shows once again that the sheer number of calculations in all of this can be quite mind-boggling. Even converting the 9 components of a simple tensor would require 9 terms for each calculation, 81 terms altogether for the 9 components. In 4-dimensional space-time, we would have 4 times 4, or 16 terms for each, making 256 altogether to be calculated just to convert the measurements of the components of one tensor from one frame of reference to another. Thank goodness for the summation convention, which seems to put things so simply, as long as we can get used to what it means. Here once more are the 4 such summation formulae which might apply in different situations of upper and lower indices for a tensor, or rather a dyad. Now, all of that discussion started off by suggesting that 2 vectors v and w could be written down using either their contravariant or their covariant components, and then be multiplied together via the tensor product to give this tensor. In other words, they could produce different versions of the tensor with different mixtures of upper and lower component numbers. They were in a sense the same tensor, produced from the same 2 vectors, and yet their components were very different. And so when transforming them from one frame of reference to another, they had to be handled very differently, depending on the upper or lower indices of the tensor. Another extremely important way in which tensors with differing upper and lower indices have to be handled very carefully is when taking their derivative, their covariant derivative. You should by now realize that at some stage tensors will probably need to be differentiated with respect to position in space, and of course eventually with respect to space-time. From what we discussed in video 7, it should be no surprise that finding such a derivative will not be a simple case of using ordinary differentiation. We will always need to use the covariant derivative. As we discuss this now and apply what we did for vectors in video number 7 to tensors, we will realize another very important but simple fact about the covariant derivative. With vectors, we realized that we needed a new type of derivative, the covariant derivative, if we wanted to calculate the way a vector actually changes with position, if it does change. This was because in the likely event of having to use curvilinear coordinates to make measurements of some space or other, the basis vectors would also be changing with position, so that if we use the straightforward differential, the measurement would probably not be correct. The solution was to bring the metric tensor into play. The metric tensor, if you recall, explains how the basis vectors change over the space, and this was brought into the equation for the derivative as a compensating factor and involved what are called Christoffel symbols. That was the essence of the covariant derivative. We ended up with two expressions for the covariant derivative depending on whether we were dealing with contravariant components of a vector or covariant components of a vector. These two expressions or types of covariant derivatives are probably best written down using the Einstein Summation Convention, where, if you recall, we had for a vector v that the covariant derivative of the contravariant or upper components of the vector is given by this, with a plus sign here, and that the covariant derivative of the covariant or lower components of the vector is given by this, with a minus sign here. Now you might need to look at these carefully to remind yourself of what's what and get your head around things before we think about applying these ideas to tensors. In 3 dimensions, this represents 9 equations. M and n each run from 1 to 3. Also, within each equation, r, which is the only thing that is summed over on the right-hand side, is also 3. And so each equation will have 3 terms with Christoffel symbols in them. On top of that, those Christoffel terms will be full of expressions with the metric tensor and its partial derivatives, which together will produce the compensating factor. Here's the first of those 9 equations for the covariant derivative of the contravariant component of a vector v in 3 dimensions, written out in a little more detail. It is the covariant derivative of the contravariant component of v1 with respect to x1. This, of course, would look far more complicated if we wrote in the details of the 3 Christoffel symbols. Remember that once calculated for a particular point in space, this covariant derivative of the contravariant component v1 of the vector that exists at that point will not change when a different frame of reference is used to measure the same thing. This is because the Christoffel terms will take into account all the stretches and twists and turns of any other reference frame. And if you think about it, in these 3 dimensions, this equation is the first of 9 equations for the covariant derivatives of the contravariant components, and there will of course be a further 9 for the covariant derivatives of the covariant components. Now, before we move on to ask and answer the question as to how we can take a sensible and therefore invariant derivative of the components of our tensor t in any of its forms, upper, 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 lower, lower, upper, or lower, lower, we need to delve just a little more deeply into the idea of a derivative, and particularly that of the covariant derivative. I will state as a fact for now, and then justify it as we go along, that the application of the covariant derivative of a tensor not only gives a true representation of the value of the derivative of the tensor components, which is independent of the frame of reference, but the result of taking the derivative will always be a new tensor of 1 rank higher than before the derivative was taken. Not only that, the extra rank will show itself as an extra covariant or lower index in the new tensor. In simple terms, what that means is this. You take a tensor, say Tmn, both upper, which in 3 dimensions would have its 9 components in a matrix. You find the covariant derivative of it, of all its components, and you end up with a new tensor, let's call it S, which is the derivative of the old one, but it also has an extra lower index. It would be a rank 3 tensor. The rank of the tensor has been increased by 1 in the process of taking the covariant derivative, and we have an extra lower or covariant index. Now, we haven't talked about tensors of rank higher than 2 as to what they might actually look like, so let me approach that idea slowly. Let me first work through a very simplistic justification of the idea that taking the covariant derivative will increase the rank by 1, and that increase will show itself as a new lower covariant index. Let's go back to square one. Consider a scalar field throughout a three-dimensional space. Explicitly, let's take the gravitational potential of Newtonian gravitation that we discussed earlier in video 1. This is indeed a scalar, being the potential energy per unit mass at a point in the space. It therefore has no direction. By the strict definition, it is a tensor of rank 0. That's what scalars are. When we looked at it, we considered it as a function of the distance away from a large mass like the Earth, the distance being r, the radius, and we gave it the letter phi. We'll steer clear of x1, x2 and x3 for the moment and just look at a single distance variable, the radius. In discussing this in video 1, we also showed that the derivative of this scalar with respect to distance r in this case was a vector, the acceleration due to gravity or the gravitational field strength, little g. This vector, little g, is a tensor of rank 1. It's a vector. And so taking even the ordinary derivative of the rank 0 tensor, phi, has changed it into a rank 1 tensor, little g, something with size and direction, a vector. It has increased the rank by 1. If we thought about this in 3 dimensions and used x1, x2 and x3 instead of r, we would find a similar result, and it would be clear that the 3 components of the new gravitational field vector little g were definitely covariant. They had been created from differentiation with x on the bottom. Now that's a fairly loose argument, but I think it should persuade you that taking the derivative of a rank 0 tensor, a scalar, produces a rank 1 tensor, a vector, and that the extra rank must be shown in the components as a lower index, a covariant index. We essentially went from rank 0 to rank 1, scalar to vector, by differentiation. So let's now consider the same idea again, but this time going from a vector to a tensor, or rather from a tensor of rank 1 to a tensor of rank 2. We will start with a vector v in 3 dimensions, and we'll consider as usual writing it out using its contravariant components with upper indices alongside the usual basis vectors e1, e2 and e3. V, the vector, is v1 e1 plus v2 e2 plus v3 e3. And we know from video 7 that generally if we wanted to take the derivative of this vector with respect to displacement, we must use the covariant derivative. This will take into account any stretching and bending of the coordinate system which might be being used. In summation form, the covariant derivative of the 3 components v1, v2 and v3 is given by this equation. And writing this out for the 3 dimensions would mean we have 9 equations, 9 derivatives for the various 3 contravariant components differentiated with respect to the 3 dimensions x1, x2 and x3. The red ones here represent the derivatives of the component v1 by x1, x2 and x3. The blue ones represent the derivatives of the component v2, and the purple ones represent the derivatives of the component v3. At this point, we don't really need to think about the details of the 9 equations, in other words, how we would calculate the right-hand side. We only need to be aware that in taking the covariant derivative of a vector in 3 dimensions, we get 9 derivatives or components. We could spread these 9 things out in a 3 by 3 matrix like this, where we've kept the colour coding. And they are, in a sense, the 9 components of the new thing that has been created by taking the covariant derivative of the 3-dimensional vector v. Each one of these 9 things is a function of position, a function of x1, x2 and x3. And it should be fairly obvious, therefore, that this all represents a rank 2 tensor, a kind of 3 by 3 matrix. And so we could write these components like this, where once again we've kept the colouring to help clarify the situation. The 9 components here have the upper index of the old vector v, 1, 2 and 3 for the 3 dimensions, and they have the added lower index from the covariant derivative, again 1, 2 and 3. It would seem therefore that taking the covariant derivative of the vector v, a rank 1 tensor, has produced a tensor of rank 2, and that the extra index is a covariant index, a lower index. So as we said before this discussion, the application of the covariant derivative to a tensor, whether it's a scalar or a vector or some higher rank tensor, not only gives a true representation of the value of the derivative of the tensor, which is independent of the frame of reference, but the result is always a tensor of 1 rank higher than before the derivative was taken. And not only that, the extra rank shows itself as an extra covariant or lower index in the new tensor. Bear in mind that this rank 2 tensor here was not produced by multiplying 2 vectors together via the tensor product, which is how we introduced the idea of tensors. It came about from taking the derivative. Now I should, I suppose, remind you that we do, of course, have a further 9 equations which would apply if we had started off considering the covariants or lower components of the vector v. If this equation for the covariant derivative of the covariant components of the vector v were to be evaluated, we would end up with a different 9 component values of the tensor t, which would of course then have 2 lower indices, one of which would have come from the original vector v, and the other from having taken the covariant derivative. The idea that the application of the covariant derivative on a tensor produces a new tensor of higher rank has what you might call one exception. It may surprise you to hear that the covariant derivative of the metric tensor is always 0, and I mean any metric tensor. Take as an example this 2-dimensional space, flat or otherwise, and suppose it's being measured using these curvilinear coordinates. It clearly has a metric tensor which is changing from place to place in the directions of the axes and in the stretches of the basis vectors, and yet the covariant derivative of it is 0. The covariant derivative, at least on the face of it, seems to be saying that the metric tensor is not changing. It is constant everywhere. Now this might seem particularly weird to you at first, especially as we'd said that the covariant derivative always gives the correct rate of change of things at a point in a space. But this is the one exception, and it's obvious when you think about it. When we discussed the covariant derivative in video number 7, we use the casual language to say that it takes the ordinary derivative and then adds or subtracts a term to compensate for the fact that the metric may be changing. It compensates for any curves and stretches in the metric. That means that when the covariant derivative acts on the metric tensor itself, it takes the derivative of it and then compensates for those same changes in the metric tensor. In a sense, it subtracts what it's just calculated, and so for any metric at all, the covariant derivative of the metric tensor is always 0. Now we won't explore this any further here, but it may interest you to know that you can use this simple fact to derive fairly easily the formula for the Christoffel symbols. Anyway, as a final thought on this topic of taking the covariant derivative of tensors, we should at least look at what would happen if the covariant derivative of a rank 2 tensor were to be calculated. So, for example, if we started with a rank 2 tensor t, which had one upper and one lower index, and we took its covariant derivative, we would obtain a rank 3 tensor s, which we can illustrate in this rather simplified shorthand form. See how a new covariant index has been produced in the resulting tensor. In 3 dimensions, this new tensor S would have 3 times 3 times 3, 27 components in it. It would be a bit like, I say a bit like, having 3 rank 2 tensors at every point in a 3-dimensional space, or if you like, 27 components at every point, 27 numbers, scalars, at every point in the space. Illustrating such a set of components for this tensor would be difficult. We would have to try and do it using a 3-dimensional matrix. Here's my best attempt to show the 27 components of the rank 3 tensor S in this particular case. Each point in space, therefore, has 27 numbers, 27 scalars associated with it. And even in 2-dimensional space, a rank 3 tensor could only really be illustrated using something like this. With a 2 by 2 by 2 matrix array, there will be 8 component measures at each point in the 2-dimensional space. Finally, after all this rather abstract discussion about tensors, it might be good to finish this video with an example of a real tensor which we may come across in later videos. Without much explanation, therefore, let me first give a version of what can be called the electromagnetic tensor. We'll have to look at it in 4-dimensional space-time, which means we will take x0 as time, x1 as the x direction, x2 as the y direction, and x3 as the z direction. And we'll continue to assume that this space-time is flat. In other words, there are no significant masses in it, and also we'll assume that the coordinates are not curvilinear. The metric tensor for those coordinates would be what is known as the Minkowski metric, and would be written using the Greek letter eta rather than g. In one of its forms, the Minkowski metric can be written like this, where we've used Greek letters mu and nu instead of m and n. I'm sure you can see by now that as far as we're concerned, this is not only saying that the space is flat, but also that the measurement system is basically Cartesian, and that comes from the diagonal 1s and the off-diagonal 0s. With those provisos, therefore, the covariant version of the electromagnetic tensor, which is usually given the letter F, can be shown to have these 16 components, 16 values at each point or event in space-time. I say covariant version because the 2 indices here are in the lower position. We could, of course, change either or both of these to the upper position by using the metric tensor. For example, the wholly contravariant version of the electromagnetic tensor would be found by recalculating each of the 16 components by application of the metric tensor twice. Think for a moment about how this equation could be used on each component of the electromagnetic tensor in turn. For example, the new F11 upper in the top left-hand corner will be found by first putting mu and nu both equal to 1 and then summing over the lambda and rho from 0 to 3, and that would give 4 by 4 equals 16 terms to be added together to produce that first component in the top left corner, F11 upper, and it would include all 16 of the F lambda rho lowers. Anyway, going back to the covariant version of this electromagnetic tensor, if we take the speed of light equal to 1, it can be made to look much simpler. Notice the electric and magnetic field values in this, those of Ex, Ey and Ez, and Bx, By and Bz. Notice also that this particular tensor is antisymmetric, which means f mu nu equals minus f nu mu, so that the diagonals are all 0 and the off-diagonals are mirrored with negative values. Now, if you've done Maxwell's equations and the Lorentz force in the dark and distant past, you may be vaguely familiar with the electromagnetic force potential A, or A mu, and of the fact that the electromagnetic tensor F arises from those equations as this expression. Now, if this is not familiar or too vague, don't worry. We should by now have a reasonable concept of what a rank 2 tensor is and how such things can be manipulated. And there's 4 things we should be basically aware about. Number 1, how they can be produced from the tensor product of 2 vectors or by taking the covariant derivative of a vector. Secondly, how their components can be transformed to those in another frame of reference and still represent the same tensor. Thirdly, how their covariant derivative can be calculated and the likely consequence of that. And fourthly, how different versions of them, upper, lower indices, can be found by using the metric tensor. We should now be in a position to think a little more about general relativity. However, before that, there's perhaps a need for some revision of the basic ideas of special relativity, and that will be covered in the next video, number 10. Having looked at various ideas associated with tensors in this video number 9, in the next video number 10 we'll change tack and have a brief revision of some of the ideas of special relativity, those which we will need for when we move towards general relativity.